Graphs of polynomials. We do this for every single unit. So what we're going to do is we're going to graph this polynomial function here. And by graphing it, I'm just going to put it in the calculator. So we already have it put in. We're going to graph it. And we have to find the roots. Easiest way to find the roots. Second trace, 0. Zeros and roots. It's going to be about the same. Left bound, right bound, guess. And that is close to 2, 0. So one of my roots is at 2, 0. Looking back again, there's another root over here. Another root is at negative 2, 0. And 2, 0, this actually has a multiplicity of 2. Because we look at the graph, comes down, hits the x-axis, goes back up as a turning point on the x-axis, so it has a multiplicity of 2. To find the y-intercept, easiest way to find the y-intercept, you can do this again on the graph if you want. You could, but the easiest way to do this is just set the x equal to 0. So if I set x equal to 0, minus 2 times 0 squared, you should have the answer before I even write all this out. Setting everything equal to 0, this is all 0 except for plus 8. So the y-intercept is at 0, 8. The vertex, well, there is no vertex of this polynomial. There's local minimums and maximums, but when polynomials, unless it's a quadratic, it doesn't have a vertex. So these little maximum and minimums here, those are called local minimums and maximums. They're not actual vertexes of the polynomial function. So what is the vertex? Put none. The domain is the x values. So there's no breaks in the graph, so there's no stopping points. Domain is all real numbers. So all real numbers. Range, looking from the lowest point to the highest point. The graph continues from negative infinity, and it keeps on continuing to infinity, so the range is, y is all real numbers. Increasing interval is where it might be good to know local maximums, minimums, and maximums. So I want to know this maximum up here. So I go second trace, maximum, left bound, enter, right bound on the right side of the maximum, enter, and I have it at negative 0.6 repeating, and we'll say 9.5. So that's the local maximum, negative 2/3, and 9.5. So that's down here. Negative 2/3 and 9.5. And then local minimum will be down here, and you can check left bound of the minimum. So I just did minimum here. Right bound, enter, move it a little closer, 2, 0. So local minimum is at 2, 0. So when I'm looking at the graph, this is increasing to negative 2/3, decreasing from negative 2/3 to 2, and increasing again from 2 to infinity. So increasing interval would be from negative infinity on the x to negative 2/3. and from 2 on the x values to infinity. It is decreasing from negative 2/3 to 2. The axis of symmetry. There is no axis of symmetry when it comes to a polynomial, so this is none also. And end behavior, always end behavior. So as x goes to negative infinity, what's happening to the y values? They're going down to negative infinity. And as x goes to, so this is negative infinity. And then we have, as x goes to positive infinity, what's happening to the y's? They're going up to infinity. Now, if this is still confusing to you, there's another way to do this with end behavior. If you go to second graph, and we look at the x values, as x goes to negative infinity, so I'm going up, what's happening to the y values? Where are they going? They're going to negative infinity. They're getting bigger negatives to negative infinity. So that's where negative infinity comes in. As x goes to positive infinity, so let's go look at positive infinity. So as we're getting closer and closer going to positive infinity on the x values, what's happening to the y's? They're getting bigger. They're going bigger to positive infinity. So you can also look at the table. I like to look at the graph. I believe in looking at the graph is a much better way to look at it. Come to class with any questions on this. Thanks.